let A be an n by n matrix. And I want to think of it in this lesson as a linear transformation. In other words, it takes a vector u in Rn to the vector Au, which is also in Rn, because A is n by n. Just as in the last video, let B equal to v1 through vn be a basis for Rn. Question: is there a matrix A prime with Au with the coordinate vector of A times u with respect to that basis equal to A prime, that's an equal sign here, equals A prime times the coordinate vector of u with respect to the basis? Let me box that because that's an important question. Now, let's go and answer that. By the theorem from the previous video, we know that u is equal to v1 vn, that partitioned matrix, times the coordinate vector of u with respect to the basis. And we also know that we can do the same thing with A times u, because A times u is also a vector in Rn. So it is equal to v1 through vn times Au b. Now, so I don't have to keep writing this partition matrix, I'm going to call it, just for this video, P. By Tim, we know that P is invertible. So Au, the coordinate vector of Au with respect to B, is equal to P inverse times Au. That's using the second equation over here. Now let's sub in this equation for u to get, well, for u on the right hand side, to get Au b is equal to P inverse A times Pu. This brings us to our definition. This guy right here, we call this notation is not in the book, I don't think, but this is what I'm using. I'm going to call this guy right here, brackets A sub B. So it is, I guess, the matrix of A with respect to the matrix, which matrix? It's the matrix of A with respect to the basis B. So in other words, what we've just shown using this notation that I just introduced is the following theorem. Let B be a basis of Rn and let A be an n by n matrix. If u is any vector in Rn, then the coordinates of Au with respect to the basis B is the matrix of A with respect to the basis B times the coordinate vector of u with respect to the basis B. Let's do an example. Consider the basis 1, 1, 1, 2, and the matrix A equals -2, 2, 2, 3. I've given names to the basis vectors because I want to refer to them specifically. Using our theorem, we know that the matrix of A with respect to B is 1, 1, 1, 2 inverse times -2, 2, 2, 3 times 1, 1, 1, 2, which is equal to, after you do the work, minus 2, 0, 0, 2. I want to point out that this matrix right here is diagonal. So we've effectively just diagonalized this matrix A that we started with. And this idea is what we're going to be working with in the next couple of lessons. The idea being that by changing coordinates in the right way, we'll end up with a diagonal matrix for most square matrices.